So in this video we will introduce the moment generating function, and then we'll get some practice using the moment generating function and finding one for the binomial distribution. So first I think it's important to get some definitions down. So the first definition we'll look at is the definition of a moment. So for any integer n, the nth moment of x, where x is some random variable, is defined as the expected value of x raised to the n. And notice that n that I'm talking about here is, the random variable is raised to that n, not the expectation. So of course when n is equal to 1, this is just the expectation of x, which is the mean of x. But we can consider, when n is equal to 2, we have the second moment, and so on. And we also might want to define the nth central moment. And the central moment just means that we subtract off the mean of the random variable. So here we have the random variable x minus its mean, which of course is just the expected value of x. Mu is just shorthand for the expected value of x. So we've got x minus the mean raised to the n, and then in expectation. And the second central moment, so if we let n be equal to 2, this is just the definition of the variance. Okay, so with those definitions in mind, let's think about the definition of a moment generating function. And we'll see why the moment generating function has this name. Namely, we can use it to generate moments of a random variable. So let's suppose we have a random variable x. It has a PDF f of x. We define the moment generating function to be, so notation will be m subscript x, and it's a function of t, so it's a function of some variable t. So it's defined to be the integral of e to the tx times the PDF of x dx. And another way to write this is that this is just the expectation of e to the tx, where x is our random variable, with PDF f of x. All right, so the moment generating function is just defined as an expectation, or equivalently an integral, or a sum if it's a discrete random variable. So it's an expectation of e raised to the tx, where x here is the random quantity, t is just this variable. All right, and then, as is typical in this course, the bounds of this integral I'll leave out, but the indicator function inside of this PDF will set the bounds. So if you're working with a uniform distribution, the indicator function will set the bounds to be a to b. If it's an exponential distribution, it'll be from 0 to infinity. That'll be incorporated in this PDF. All right, so let's try an example of finding the moment generating function of x, where x is binomial np. So in this case we have a discrete random variable, and that means that our moment generating function, it's still an expectation, but the expectation will be a sum rather than an integral. So the expectation of e to the t times x, and this will be a sum over all of the relevant values of x here. That'll be 0 up through n, and should be e to the tx times the probability mass function of x. So remind yourself, what is the probability mass function of x, where x is binomial? Well, that should be n choose x times p raised to the x times 1 minus p raised to the n minus x. All right, so we'll fill that information in. So we'll have the sum from x equals 0 up through n, e to the t times x, and then we'll have our n choose x, p raised to the x, 1 minus p raised to the n minus x. All right, this looks kind of ugly, but there are some simplifications that we can make in order to simplify this. So we have the sum from x equals 0 up to n. So the first thing that we'll do is we will combine these two terms. They don't look like maybe they're easily combinable now, but if we think about this first term as e to the t all raised to the x, then we can combine it with this term, which is raised to the x, and combined it would be e to the t times p all raised to the x. And I'm actually going to move that over. So I'll put that here, and I'm going to put the n choose x here, and we'll see why in just a minute. And then we've got that last term, which is 1 minus p to the n minus x. Okay, so my claim is that this will be equal to e to the t times p plus 1 minus p all raised to the n. And this should follow from a theorem that you probably learned in calculus that says, say if you have a u plus a v raised to the n, that's equal to the sum from, say, I equals, well, we'll do it in terms of x equals 0 up through n. This would be n choose x, so the n here is the same as the n here. The x here is what you're counting through from 0 up to n. And then u to the x times v to the n minus x. All right, so what we did was just use this formula where our u was e to the t times p, and our v is 1 minus p. All right, so we had this, and we moved back to this here. So this is a nice form of the moment generating function for a binomial random variable.